Welcome to this revision video about waves, currents and tides. All three of these things are very important inputs into the coastal system, and in this video we're going to examine the characteristics of each of these three inputs. First thing to consider is the importance of waves and also how they're created. So waves result from the friction of the wind blowing over the sea. So as the wind blows across the surface of the sea, energy is transferred from the wind into the water as a result of friction. Waves can then be affected by a number of factors. So the size of a wave, for example, could be affected by the speed of the wind. It goes to reason that the stronger the wind, the more energy is going to be transferred to the water, and therefore the larger the waves are going to be. Can also be dependent on the duration that the wind has been blowing for. So if the wind has been blowing for a long time, that is going to mean that more energy has been transferred into the water. The third factor is what we call the fetch, and this is illustrated by the diagram on the right hand side of the screen. The fetch is defined as being the distance of water that the wind has blown over in order to create the waves. So in the case of maybe the southwest of England, particularly places like Cornwall, down here we can see that the waves reaching that part of the coastline in the UK could have travelled across the entire Atlantic Ocean. That would mean if the wind was blowing across the whole Atlantic Ocean, again that's going to be transferring more energy to the water. However, if we think about the south coast, so Dorset for example, the waves hitting here are likely to have only come across the English Channel and therefore are going to have a much shorter fetch. The wind has had less opportunity to transfer energy to the water and therefore to increase the size of the waves. So waves with a longer fetch tend to have more energy than those with a shorter fetch. Also, as the wave approaches the beach, the waves can be influenced by the topography of the seabed. So if the seabed is quite flat or quite gently sloping, then we're going to have relatively gentle waves because that energy is going to be lost a little bit further out to sea and the waves are going to slow down more gradually. Whereas if we have a steep beach, then the waves are not going to slow down at all until they get very, very close to the shoreline, and that produces what we call plunging or destructive waves. It's also important that we have a good understanding of the anatomy of a wave and the relevant bits of terminology that go with that. So let's imagine for a moment we have some waves out in the ocean. I'm just going to draw some waves here. And we need to be aware of the different features and characteristics of these waves. So the first thing to note is that the top of the wave, this point here, we call this the crest of a wave, and the bottom point here we call this the trough. Now normally, under normal conditions, if that wave wasn't there, then the sea level would be relatively flat. The highest point is the crest, the lowest point is the trough, and the distance between the crest and the trough, we refer to that distance as the wave height. So the wave height is the difference in height between the crest and the trough. Sometimes you may come across the word amplitude, and that is half the wave height. Basically the difference in height between where the water would be if it was flat and where the crest or the trough of the wave is. So the amplitude is half the wave height. The other feature that we need to be aware of is the wave length. So if we were to look at the distance between those two crests there, that is what we call the wavelength. So the distance between one crest and the next. And this links a little bit with the frequency of waves. So the frequency, we can't necessarily represent this on the diagram, but it's the number of waves per minute. The crest is the highest point, the trough is the lowest point, and the wave height is the distance between the crest and the trough. The wavelength is the distance between two wave crests, and the frequency is the number of waves passing a particular point per minute. The other thing that we should understand as well is how waves move and how they break, a process that we call shoaling. So you can see here that if we look at these waves, the water is moving in a circular motion. We can see that an individual water particle, if we were to track its movement, as the energy moves through the water is moving in a circular motion. The water is not flowing towards the land. The water is just moving in a little circular motion. And as we go down through the water, that motion continues, but it gets less and less. As we go deeper and deeper, there is less movement of that water until eventually we will reach a point where that water is not moving. We can link this back actually to what we looked at in the last video, which is the difference between whether the waves are touching the bottom of the seabed or not. So at this point here, the deep water waves are not affected by the seabed. This would be that zone that we call the offshore zone. Whereas where the waves start to touch the seabed, as they are here, this would become then the inshore zone here. Now what happens as the waves start to approach the coastline is that the bottom of the wave will start to hit the seabed and there will be friction with the seabed. And what that does is it slows down the bottom of the wave, but the top of the wave carries on moving at the speed it was before. So rather than that nice circular motion that we have of the water here, the movement of the water becomes a little bit more elliptical, a little bit more stretched out. What this will do is it will cause the wavelength to get shorter and it will cause the wave height to increase. So we see a shortening of the wavelength. The waves basically get closer together. And we see an increase in the wave height. So basically the waves get bigger. And we can notice this if you think back to maybe when you've stood on the beach and you've looked out to sea. You can't see those waves approaching far out in the distance. They don't look as big. Okay, and then as they get towards the beach, they start to increase in height. And then eventually the top of the wave, the crest, will become unstable and that will collapse. And that's why the waves break. The movement of water up the beach, when the wave breaks and the water rushes up the beach, we have a name for that. We call that the swash of the wave. And then when the water returns back to the sea and flows back down the beach, we call that the backwash. So there's some important bits of terminology to remember there. Not all waves are the same, and we need to have a good understanding of the differences between constructive and destructive waves. So a constructive wave, or a series of constructive waves, tend to have quite a long wavelength and therefore quite a low frequency. We might only expect 8 to 10 waves per minute with constructive waves. We can see that on this diagram. The waves are relatively spaced out, and they also have a low wave height, maybe less than a metre or so. Still have that circular motion of the water, but the waves are more spread out. They tend to be lower and they tend to be gently sloping. They're not as steep. When they reach the beach and they start to break, they break in a way that we call surging and spilling. Basically, the front of the wave spills gently down the water in front and swashes up the beach with quite a strong force. So the swash is quite strong. Most of the energy in a constructive wave is used to push material up the beach. Okay, so the water spreads quite a long way up the beach, pushing material with it. So it acts almost like a little bulldozer pushing material up the beach. Very little of that energy is actually transferred to the backwash. So most of that energy runs out on its way up the beach, meaning that these waves have a weak backwash. They're not bringing as much material back down the beach as they are pushing up the beach. Destructive waves, on the other hand, have almost the opposite characteristics to constructive waves. So they have a short wavelength. The waves are much closer together. And that means they therefore have a high frequency, maybe 10 to 14 waves per minute when we think about destructive waves. They've still got that circular orbit, but this time the waves are much steeper. They break in a motion that we refer to as plunging. So rather than spilling gently down onto the beach, the energy is actually transferred downwards. It's almost like a scooping action of the wave. They have quite a high wave height. They're over a metre, sometimes maybe 2 to 3 metres in height during storms. And because of that plunging effect, the energy is directed downwards. So the energy of the wave is focused down onto the beach. Okay, and as a result of that, there's a very strong backwash, which results in erosion. So this has, rather than a bulldozer kind of pushing material up the beach effect, like constructive waves do, destructive waves have more of a scooping action, and they are removing material from the beach face, eroding it out to sea, perhaps depositing that material offshore, so creating what's called an offshore bar. We will look at those in a bit more detail in a future video. So these are the main differences really between constructive and destructive waves. Destructive waves are more frequent, they have a shorter wavelength and a taller wave height. That means that they result in erosion from the beach, whereas constructive waves, with their longer wavelength and their shorter wave height and their stronger swash, result in deposition happening on the beach. A good example of constructive waves here, approaching a beach in Cornwall, and we can see that we've got these lines of waves relatively widely spaced, and we can see that they are breaking quite gently. This is a good example of that effect of spilling, where the wave, the water breaks down the front of the wave quite gently. This is why they're quite popular for surfers. And the waves are relatively widely spaced. They're not particularly high, and because of the gently sloping beach, those waves are starting to break quite some distance from the shore, which means they lose quite a lot of their energy before they actually reach the shoreline. Destructive waves, on the other hand, here's a good example of that plunging effect. This is on Chesil Beach in Dorset. We can see that that wave is forcing its energy downwards onto the beach there, resulting in that strong backwash. Now, we can't say that any particular beach experiences either just constructive or destructive waves. It obviously depends a little bit on what the weather conditions are doing and the fetch of the waves that most commonly hit that beach. But it's very common that beaches actually go through a little bit of a cycle of constructive and destructive waves. And this is another good example of the concept of feedback. So, for example, we might find that constructive waves are building up the beach. So by pushing material up the beach with their strong swash, they're going to make the beach steeper. As we know though, a steeper beach means that the waves are more likely to then become destructive. So the constructive waves have made the beach steeper, which maybe makes the waves more likely to be destructive. Those destructive waves will erode the beach, making it less steep, which then causes that pattern of constructive waves to resume. And those constructive waves will make the beach steeper, maybe triggering destructive waves. So we have this cycle of negative feedback where the constructive waves are creating destructive waves, which in turn are creating constructive waves. So things are in a nice dynamic equilibrium on this beach as a result. Waves are not the only input of energy and sediment into a coastline. Currents are also important as well, and currents can form in a number of different ways. The most common is what we call longshore currents or littoral currents. You'll have come across this before as the process of longshore drift that we can see annotated in this diagram here. So the waves approaching the beach at an angle, and that generates a flow of water running parallel to the coastline. So as a result of that zigzagging of material, water and sediment is moved along the coastline as a result of that longshore current. Rip currents are very strong currents that move away from the shoreline. So in this diagram here we can see that we've got this strong current that's flowing away from the beach. This is caused when you have lots of waves coming in, so quite high frequency destructive waves coming in, hitting the beach, and that water is kind of piling up against the beach. It doesn't have anywhere to go and will find a route back out to sea in a relatively narrow channel. So you get this quite strong current dragging the water offshore. This can be quite dangerous for people who are swimming or surfing along a beach, and you can find yourself very, very quickly pulled out to sea. So rip currents are an unusual current that moves away from the shoreline. The final current that we need to be aware of is the process of upwelling. We can see this happening in this diagram here, where the wind has blown the surface water in one direction, which has almost created a little bit of a gap really to allow water to well up from deeper in the ocean. This happens often on the edge of continents, and the wind driving the water away creates that space for the cold water from deeper in the ocean to move towards the surface. This is a really important part of the circulation of our oceans. Our oceans are moving around in a constant, almost conveyor belt like loop as the water is moved along the surface and is cycled between the surface and the deeper part of the ocean. A really important process that we need to understand when we think about waves is the process of wave refraction. This is basically where waves bend as they approach the shoreline, because part of the wave is slowing down when it reaches shallower water, and the rest of the wave is carrying on moving at quite a fast speed because it's in relatively deep water. So I want us to imagine the situation that we've got here. This is refraction on a straight coastline. So I want to imagine our waves are coming in at a little bit of an angle. They're moving in this direction here because maybe the wind is also blowing the waves in that direction as well. So we imagine our prevailing wind blowing the waves in at an angle. Now what will happen is eventually, as the wave gets towards the shoreline, it will reach the shallow water. So I want you to imagine this dotted line here is where the water is quite shallow, but out here the water is still relatively deep. Now what will happen is, as part of that wave reaches the shallow water, it will slow down. So the wave here will be going relatively slowly, but the same wave further over here will be going relatively quickly. What happens as a result of it slowing down here, and we can see this as we trace these three lines across this diagram, is that the wave bends and it refracts. So the wave curves around, eventually becoming parallel with the shoreline, but this end of the wave is hitting the beach before this end of the wave. What that does is it helps to create this longshore current, this littoral drift, this longshore drift that we've talked about before. So that's how wave refraction works on a straight coastline. It does a similar thing on a headland as well, which helps us to understand why the energy of a wave varies between headlands and bays. So again, I want us to imagine that each of these lines is a wave approaching the coastline, or even the same wave in different stages as it approaches the coastline. Out here, the water is going to be relatively deep on this side and relatively deep on this side. As it gets towards the headland though, the water is going to get shallower. So I want us to imagine that the water here is relatively shallow in comparison to the deeper water here and the deeper water here. What happens as a result is that the wave approaching the headland will slow down, and the wavelength will get shorter, the waves will get closer together. Whereas over here, the waves will continue to move relatively quickly. What this does is it causes the waves to bend, and we can see if we trace one of those lines on here, we can see the wave has bent to almost mirror the shape of the coastline. Same with this one here. It's not quite as bent because it's still a little bit further out. But we can see that the wavelength is shorter here than it is here. The waves are further apart in the bay and closer together at the headland. What this does, which is indicated by these blue arrows here, it focuses the energy of the wave onto the headland. So the energy of these waves coming in is directed towards the headland rather than the bay. Okay? What this means is in the bay we tend to get quite low energy waves, which encourages lots of deposition. That's why we have a beach forming in these bays. The headland is absorbing the impact of this high energy waves, or these high energy waves coming in are hitting the headland, deflecting the energy away from the bay on either side. This also does then create some of these longshore currents that we can see here, because that water is flowing away from the headland and the energy is being pushed towards the bay, also helping to move sediment into the bay away from the headland. So the depth of the water being shallower off a headland than it is at the same point in the bay means that the waves slow down as they approach the headland. The wave refracts and it bends, and that energy is concentrated on the headland. So we've got a little explanation of this here, just to help this be nice and clear for you. So as part of the wave reaches the shallow water, it slows down. That's the bit near the headland. While the part of the wave in the deeper water will continue to move quickly. This causes the wave to bend and the wavelength to shorten, and the overall effect is that the wave energy becomes concentrated on the headland, which is then going to result in greater erosion. The bay, however, where the wave energy diverges, means that the waves lose their power there and deposit sediment, which helps with the build-up of a beach. The final input into the coastal system, particularly in terms of energy, is that of the tides. So the tides occur as a result of the periodic rise and fall in the level of the sea. That's what the tides are, and they are the result of the gravitational attraction of the moon and the sun on the oceans. The moon and the sun are basically pulling on the water and pulling it off the surface of the earth, causing basically a bulge in the oceans closest to where the moon is. There's also another bulge on the other side of the earth, which creates the two high tides, and the water draining from the areas in between creates the low tides. Now we can see this on this diagram here. It looks quite complicated, but we're going to break this down into a few stages. First thing to remember when we think about the tides is actually that the moon is the main influence on the tides. The sun does have an effect, okay, but the sun either enhances or diminishes the effect of the moon. Okay, so we want to think about what the moon is doing initially, and then the sun is either helping that or hindering that in some way. Okay, so in this example here we've got the moon and we've got the sun, and both the moon and the sun are going to be pulling the water from the surface of the earth outwards. Obviously it's very exaggerated in this diagram so we can see the difference, but hopefully you can see that bulge of water here, and that's caused because the moon is pulling the water upwards off the earth's surface, creating a bit of a bulge. Okay, it also pulls the earth towards the moon as well, leaving this water behind, okay, which is why we get this bulge on the other side of the earth as well. Now where the sun and the moon are in line, the sun is also going to be helping to pull that water and pull the earth in that direction. So we get quite a big bulge here. Okay. Whereas over here, where the moon is pulling this way and the sun is pulling that way, remember the sun either enhances or diminishes the effect of the moon. So in this case, the moon is pulling in one direction and the sun is pulling in the other. So we still get a bulge, but it's not quite as big, okay, as it was over here. So we have a smaller bulge here. Same back in this situation. The sun and the moon are both pulling the water in a parallel direction, whereas over here the sun and the moon are pulling in different directions. Okay, so we have to think about whether the sun and moon are working together or against each other in terms of the size of that bulge. So the bulge creates the area where the high tide would be. I'm just going to draw another example here. So I want you to imagine we've got the earth here and we've got the moon and we've got the sun. Okay, this bulge in the water here and this bulge in the water here, okay, that's being pulled by the sun and the moon. This is where the high tide occurs. The high will be here and here, and the bits in between where there's no bulge, here and here, those points on the earth would experience low tide. Same on this diagram here, that the high tide would be where the bulges are, here and here, and the low tides would be in between at these 2 points. And the same again, high tides here and here, low tides in between. So where the sun and the moon are in line, like this, creating a large bulge in the water, this creates what we call a spring tide. It doesn't occur in the spring as in the spring months of the year. It occurs when the sun and the moon are in a straight line. Here is a good example, but also here as well, where the sun, the earth and the moon are in a straight line. Where the sun and the moon are at right angles to the earth, like this, it creates neap tides. Okay, so we have one here, we have the same situation here, where the earth and the sun and the moon are at right angles. These spring and neap tides are about a week apart. So it takes about a week for the moon to orbit a quarter of the way around the earth. So 7.5 days in total to do that. The spring tides, if you'll see here, create the highest high tides and the lowest low tides. So the difference between high and low tide when there's a spring tide is much bigger than when there is a neap tide. The difference between high and low is much smaller. So as I said, it takes about a week for any particular place to move from spring tides to neap tides and then back to spring tides again. So over here where the sun and the earth and the moon are in line, we'd have a big difference between high and low tide. The high tide would get very high up the beach and the low tide would go very low down the beach. Whereas on these neap tides, there wouldn't be as much of a difference between where the high and low tide reach on the beach or on a cliff face. If we have a look at this animation here, this shows you how, because the earth is rotating, different places on the planet are underneath that bulge at the same time. So what I'm going to do, I'm going to draw onto here where the bulges would be. Obviously I can't get the bulges to move on top of this diagram, but I want you to imagine we've got a bulge here and we've got a bulge here as well. Okay, now notice when we get to the point where we're underneath that bulge, the tide is higher, and where we're in between, the tide is lower. Okay, remember this is where our high tide is going to be, here and here, and this is where our low tides are going to be. So we can see, if we look at the corresponding level of the water below here, if we imagine that we were at this place marked by this blue line on the globe, we would be at low tide here, and then 6 hours later we'd be at high tide, 6 hours later we'd be at low tide, and 6 hours later again we'd be back to high tide. And that process would repeat every day throughout the year, moving between areas of high and low tide. Okay, so the bulge stays where the moon is, but because the Earth is rotating, different places are going to be underneath that bulge at the same time, at a different time. On the right hand side here, we've just got that explanation of spring and neap tides. It's worth remembering the difference between these. So spring tides occur when the moon, the Earth and the sun are all in a line. So again, if we had the Earth, the moon and the sun, if they were all in a line like this, then that would create the greatest gravitational pull because the moon would be pulling and the sun would be pulling in the same direction. That creates the highest high tides and the lowest low tides. So the tidal range, the difference between high and low tide, is at its greatest. Down here for neap tides, so when the Earth, the sun and the moon are at right angles, so if we had the Earth here and the moon here, but the sun was over here, then the moon and sun are pulling in different directions. And therefore their gravitational forces are interfering with each other, meaning that the bulge isn't as big, and therefore the low tide and high tide are quite similar. There's not as much difference between them. So neap tides give the lowest high tides and the highest low tides. This little animation here just shows you the movement of that bulge across the UK. So we can see that as the Earth is rotating, that bulge moves across the UK, and we can see the rise and fall in the tide, and we can see that movement of water along the English Channel, for example, or up the Irish Sea here, and we can see that difference between high and low tide. And notice how some places have a much greater difference than others in terms of the difference between high and low tide. Particularly places like the Bristol Channel here experience a very, very large tidal range. Other places, maybe like the east coast of England here, don't experience as much difference. We'll notice that sometimes the tidal limit is marked on to Ordnance Survey maps. So you can see at this point here on the map where it says MLW, that stands for mean low water. So the average point that the low water gets to, so where the low tide gets to. Obviously that's just an average, and during spring tides the low tide would be much lower. So if we take, for example, this feature here, Broad Bench, which is a wave cut platform in Kimmeridge, on average the low tide only gets to this point here. Okay, but during a spring tide, when the low tide is much lower, it's likely that that whole feature would be visible at low tide, and then at high tide the water might reach up right to the edge of that headland there. By way of trying to appreciate the amount of energy that the tides are putting into the coastal system, we can think about actually how much potential is there for renewable energy from tidal resources. So a study was conducted to try and estimate how much energy could we generate harnessing the power of the tide. So in theory, the tidal resource, if you like, the amount of energy that we could generate from the tides, is between 25 and 30 gigawatts of power. The same estimate for wave energy is about 26 gigawatts. So you can appreciate just by thinking about this that tides actually contribute a very similar amount of energy as waves to the coastal system. We sometimes just think about waves as being the most important input of energy, but actually tides are also transferring huge amounts of energy into the coastline as well. We've mentioned this phrase tidal range already, and this is just the vertical difference in height between high and low tide. So if we imagine a cross section of a beach here, the high tide reaching this point and the low tide reaching this point, the difference in height is known as the tidal range, and some parts of the world have much greater tidal ranges than others. We use these three terms here to determine to distinguish between the different types of tidal range. So macro tidal, macro meaning large scale. This is anywhere that has more than 4 meters difference between high and low tide. So the southwest of the UK is a good example of that. Micro tidal, on the other hand, micro meaning small, this is anywhere that has a very small tidal range of less than 2 meters, and somewhere like the Mediterranean would be a good example of that. Very, very small fluctuations in the levels of the tides. Anywhere with a very small tidal range will generally result in the wave energy being concentrated across quite a narrow zone, and that means that the erosional potential is much more focused on a small stretch of the beach or stretch of the cliffs, and as a result that can lead to relatively narrow beaches. Very large, wide, sandy beaches tend to occur where you have a much larger tidal range. Final thing we need to associate with tides as well are what we call tidal surges or storm surges. These occur during storms, so either during hurricanes or depressions that we get in the UK, where we have low pressure weather systems, and what they're doing is basically sucking some of the water upwards because the air is rising in a storm. What it does is it lifts some of the pressure off of the sea, and the water gets kind of sucked upwards in a little bit of a bulge. Not a huge amount, about 1 centimetre for every 1 millibar drop in pressure. So bearing in mind a deep depression in the UK might have an air pressure of 950 millibars. The average is 1,000. So, or the kind of normal setting is 1,000. So 50 millibars difference would be 50 centimetres in height. The bigger influence though is the wind. So the wind blowing down onto the ocean also amplifies the size of this bulge. You may notice this when you've maybe got a hot cup of tea that you blow onto to try and cool it down. You are creating ripples and waves in that liquid. The same thing is happening with very strong winds associated with hurricanes and storms. What happens is sometimes the storm will coincide with a spring tide. So the tide is already very high, and then on top of that you've got this additional bulge of water that is blown towards the land. The east coast of Britain is particularly prone to these, and that's because the North Sea acts like a little bit of a funnel. So you can imagine if we had a storm that was blowing this way, this bulge of water, as it gets pushed down the North Sea, the coastline is getting narrower and narrower on either side, restricting where that water can go. What happens as a result is that the water is forced to rise even further. This was demonstrated really significantly in sort of December 2013 and January 2014 down in Norfolk on the east coast. So down here a very severe storm surge occurred, and here we can see some of the impact of that storm surge, which has eroded away the cliffs and sand dunes and caused these houses to topple into the sea. So that concludes everything that we needed to look at to do with inputs into the coastal system. Make sure that you're happy with the anatomy of a wave, the difference between constructive and destructive waves, how tides work and the difference between spring tides and neap tides, and also how tidal surges or storm surges can occur.